Hello and welcome to this video on what is measurement invariance. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistics including structural equation modeling, path analysis, factor analysis, multi-level modeling and latent class analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources including workshops that I teach for QuantFish. In this video, I want to address the concept of measurement invariance, which is a concept that confuses many people. And so here I first of all want to talk about the meaning of the term measurement invariance. I will then show you where this is relevant. So in which research designs would you care about measurement invariance? We will see which statistical approaches you can use to examine measurement invariance. And I will talk about different levels that can be distinguished. And finally, I will show you how you can formally test whether measurement equivalence holds for your data or not. So let's get started and let's talk about terminology first. So what is the meaning of this term measurement invariance? That is a term that confuses many people. So invariance means not different, or you could simply say the same. And so part of the confusion, I think, comes from the fact that this is actually a negative term. So measurement invariance. So this is kind of a negative. So we could also formulate it positively and talk about measurement equivalence. And so measurement equivalence means the same thing as measurement invariance, but is a positive term and is used interchangeably in the literature. And this is a term that I personally prefer because it sounds more positive. So measurement equivalence means the measurement is the same. Now, next question that you probably will have is, the same for what? So across what is the measurement the same? And we'll talk about this shortly when I'll talk about relevance. Now let's talk about the opposite as well. So what is the opposite of measurement invariance or the opposite of measurement equivalence? The opposite would be measurement non-invariance or measurement non-equivalence, which are terms that you will also sometimes see in the literature. And those are of course highly confusing because measurement non-invariance then means, oh, it's a double negative. So measurement, it's not invariant. So this means it's different. So those terms are the opposite of measurement invariance and measurement equivalence. Now let's talk about where is this relevant? So across what are we looking to find measurement equivalence? And before we get there, one final note here is that in item response theory, we have a similar concept that's called differential item functioning, and that's actually a negative term. So this means that item parameters differ across groups, for example, differ across different cultures or something like that. So that's a related concept in the world of item response theory. Here we'll focus on the factor analytic terminology and measurement invariance as examined in the framework of factor analysis and structural equation modeling, where this is most commonly used and where it's most general because you can apply it to both continuous variables and categorical or ordinal data as well. So let's talk about where measurement equivalence is relevant next. There are different scenarios. The first scenario would be a between subjects design, meaning when you are looking to make group comparisons, as you would do, for example, with a t-test or an analysis of variance for independent samples. So you have independent groups, for example, males and females, or you have different people from different countries, different cultures that you want to compare in terms of, for example, their central tendency, their mean, and or other summary statistics such as the variances or covariances or correlation. So when you want to make group comparisons, that's one field or one area where you care about measurement equivalence because you want to make sure that you are measuring the same concepts with the same measurement or psychometric properties across those different groups. Another research area is when you have a within subjects design. So when you're looking to make comparisons across time for the same people. In other words, when you have a longitudinal study, when you have a repeated measures study where you administer the same tests or the same measures, the same questionnaires to the same people over time to look at their development across time or changes across time, then we also care about measurement invariance or measurement equivalence, because we want to make sure that we're not comparing apples and oranges across time. We want to make sure that the measurements have the same properties across time so that we can make meaningful comparisons. And that's the same idea as with a between subjects design where we make group comparisons. We also want to make sure that the different groups are comparable in terms of their measurements. And that's particularly relevant when we make cross-cultural comparisons where the questionnaires maybe had to be translated into different languages such that the different people really obtained measurements in different languages, and then the question is, do they function the same way, those measurements? Do they have the same properties in different cultures? And then finally, also a design where this is relevant is when you have multiple sources of measurements, when you have a so-called multi-rater design or multi-trait, multi-method design, where you use multiple observers, for example. Let's say you have a self-report, you have a parent report, you have a teacher report, maybe a peer report, and so forth. So then you also want to make sure that there's measurement equivalence across those different raters to make comparisons, for example, of means across those different sources or across those different observers for a given set of target individuals. So that's another area where this is relevant. So really, measurement invariance or equivalence is a prerequisite for making certain types of group comparisons or comparisons across time or raters to ensure that those comparisons are meaningful and are not apples to oranges comparisons. So you want to make sure that, for example, when you look at mean differences across groups, across time, or across raters, that those are based on the same measurement properties. That's what that's all about. So what statistical approaches then can be used to examine measurement equivalence? And so again, we're going to go through these three different types of designs, and for each one there's a different type of analysis that would be used. When you have a between subjects design where you make group comparisons across independent groups as you would with an independent samples t-test or with a one-way analysis of variance that is not repeated measures, then you would use multi-group CFA to test measurement equivalence. And so within a multi-group CFA, you specify a factor model simultaneously in multiple groups, and then you can compare those factor models, the factor structure, as well as the parameters of the factor model across those groups, including loadings, intercepts, error variances, as we will see later. When you have a within subjects or repeated measures design where you compare the same people across time in a longitudinal study, you would use a related approach. You would also use confirmatory factor analysis typically, but in this case it's not multi-group because you don't have independent groups, but instead you use longitudinal confirmatory factor analysis, which takes the repeated measures nature of the data into account. When you have repeated measures data, you have observations nested within individuals, so you have dependencies that arise from the longitudinal repeated measures data structure. So you have to use an approach that takes that into account, those dependencies or that nesting of the observations within individuals, and you can do that with longitudinal CFA. On this channel, I have separate videos that deal with multi-group CFA and measurement invariance testing within multi-group CFA that you can check out, as well as also videos on longitudinal CFA that you can also check out. And there are also playlists that you can look at for those approaches. And then finally, when you have a between sources design with multiple raters, you can use so-called CFA MTMM models. MTMM here stands for multi-trait, multi-method. So those are confirmatory factor analysis models that can be applied when you measure multiple traits or multiple constructs with multiple methods, where the methods could be raters. And so with those CFA MTMM models, you can then test for measurement equivalence across different sources or raters. And again, I have several videos on the MTMM approach here also on this channel. And I offer workshops on longitudinal CFA as well as factor analysis in general, and also a separate workshop on multi-trait, multi-method and multi-rater analysis through QuantFish that you can check out in the description if you're more interested in those approaches in particular. What different levels of measurement invariance or measurement equivalence do we distinguish in a confirmatory factor analysis model? First, or the lowest level, is so-called configural factorial invariance. Next is weak or metric invariance. Next we have strong or scalar invariance, and then finally strict factorial invariance. I will go over each one of those and explain to you what they look like in a factor model. So let's get started with a configural factorial invariance model. Here you can see an example with two groups. So this is with regard to multi-group CFA, where you would compare independent groups. But the same principle would apply also to longitudinal CFA, where you have the same factors across time as opposed to across groups. So the idea of those levels of measurement invariance are the same regardless of whether you look at multiple groups or longitudinal data or multi-rater data. So here, just to say as a prototypical example, I'm just going to use multi-group CFA because maybe that's the most common scenario where you would use this measurement equivalence testing. In this example, it's a very simple model. It's a one-factor model with three indicators. And the assumption here is that the same one-factor model applies to group 1 and group 2. And so configural invariance means we have the same factor structure, meaning the same number of factors and the same loading pattern. So if we had more factors, more than one in each group, then configural invariance would require that the same variables load onto the same factors in those groups. And that's it. So there's no requirement with configural invariance that the parameters be formally equal. So there's no equality constraints or restrictions on factor loadings or anything like that. All the parameters are estimated freely across groups, except for those that are fixed for identification, such as here in this case, for example, the first factor loading in each group is fixed to 1 to identify the factor metric, but the other loadings lambda 2,1 and lambda 3,1 are different from the loadings lambda 2,2 and lambda 3,2 here. So you can see there's an index for the group. Here's the first group has the index 1 and the second group has the index 2 as the second index, and so those are not set equal. In summary, we have a measurement equation that is group specific. So each observed variable yig, where I stands for the variable or indicator and g stands for the group, is a function of an intercept or additive constant alpha ig, and you can see it's group variable and group specific. So there's no constraint on the intercepts here, and then also there are loadings lambda ig, and again there's no equality constraint on those loadings across groups. And then there's a factor tau g, so that's the latent variable here in each group, plus epsilon ig, which is the measurement error term, which is also group specific. With weak or metric invariance, we have the same basic measurement equation, except that now you can see that the loadings lambda I no longer have an index g for the group, so they're no longer group specific. And this means the loadings are formally set equal with weak or metric invariance across groups for a given variable. So in the picture, this then looks like This, where you can see we have lambda 2 here for group 1, and then the same indicator also has a loading lambda 2 in group 2. So this parameter will be estimated to be the same. It will have the same standard error and then also the same p-value. And the same for the loading lambda 3, which is now also formally set equal across groups here. So weak or metric invariance requires equal loadings across groups, and that means, from a substantive perspective, equal units of measurement. Next is strong or scalar invariance. Strong or scalar invariance adds equal intercepts. So you can see that now the intercept term alpha I no longer has an index g for the group, so this is now also invariant or equivalent across groups for a given variable, in addition to the loadings. The loadings still have the index g dropped as well. So now we have invariant or equal intercepts and equal loadings across groups, and that is called strong or scalar invariance. Now, strong or scalar invariance is something that we often desire. That's something that is useful for us because it allows us to make meaningful comparisons of latent variable means across groups or across time if this is a longitudinal study. And that is because with strong or scalar invariance, not only are the units of measurement the same, but also the origin of measurement, the intercept, is also the same. And therefore, we can then make meaningful comparisons on the latent variable scale, and we can then compare latent variable means, which is often of interest in multi-group studies and or in longitudinal studies where we want to know whether there are any mean differences or mean changes across time. The highest level of measurement equivalence is strict invariance. Strict invariance adds the restriction of equal error variances for a given variable. So you can see here that this equation here, variance epsilon ig is equal to variance epsilon I, means that for a given variable, the error variance is the same across all groups, and that then is called strict invariance. Now, strict invariance means there's also the same amount of error variance for a given variable across groups, and that's something that's not strictly required for making comparisons across groups. However, it is a nice feature if you can show that, because it means that the variables also have a similar amount of measurement error across the different groups, and it makes your model more parsimonious. But really, to see the level of measurement equivalence that we're usually satisfied with is strong invariance, where intercepts and loadings are the same, but error variances are not necessarily the same. How do you test which level of measurement invariance holds for your data? You use confirmatory factor analysis, either multi-group or longitudinal, or a CFA MTMM model if you have multi-rater data. And with those, you can look at absolute model fit in terms of a chi-square test of model fit, as you would for a regular confirmatory factor analysis or structural equation model. So you can look at whether those models fit, and at least the configural model should fit. If the configural model does fit your data, then you can test the additional levels of measurement invariance using nested model comparisons, meaning chi-square difference tests, because those subsequent models of weak, strong, and strict invariance are nested within the configural model, and they're also nested within each other. Nested means that they are more restricted versions of the configural model, and therefore their chi-square values can be directly compared using a chi-square difference test. There are also other fit statistics that can be used to compare the models. So the usual approximate fit indices are often used, RMSEA, CFI, and so on, to test for measurement equivalence. Now, in summary, what is all this good for? So why do we need to care about measurement invariance? And once again, the reason is that we want to make sure that we're not comparing apples and oranges. We want to make sure that when we have different groups, that we want to compare, for example, with regard to their means, that we can make those comparisons, that those comparisons are meaningful. And for that, the measurement intercepts and the measurement loadings for a given variable should be the same across those different groups and or across time in a longitudinal study, so that we are in a position to make those comparisons meaningfully. And that is the whole reason why we care about measurement invariance, to ensure that group or longitudinal comparisons are meaningful, or comparisons across multiple raters. Now, there's also such a thing as partial measurement invariance. So sometimes it happens that not all variables show invariance. Maybe there are some questions that function differently, for example, in different cultures. So you have only some variables that are invariant, not others. And so then you might still be able to make comparisons if you have a sufficient number of variables that are measurement equivalent across those groups, but not necessarily all of them have to be equivalent. I hope you found this video useful to learn more about the concept of measurement equivalence. If you did, then please subscribe to this channel, and also don't forget to check out the description for additional resources, including QuantFish workshops where I deal with those kinds of topics in greater detail. And I'll see you next time.